So there's a couple of things that I want to make sure that we know fully before we jump into the test review. So 3 things I want to go over. First, recognizing the need for chain rule for certain problems. So if you can look at part B on page 39 here. So it's asking for, at the top of the page, it says find f prime of 5 for each of the following if possible. So that's our goal. Our goal is to find f prime of 5. Okay, so do we see the need for chain rule here? Okay, so we have a bracket or parentheses with multiple, or with a function inside, and you got a bracket with an exponent outside. So there's clearly the separation between the outside inside portion. So we got to do chain rule here. Okay, so this is in the chapter 2 packet that you guys have. Okay. And then we'll move into that test review packet in a little bit. So page 39, oh, sorry, page 39, numbered part D. Now, what's the outside portion? We know there's outside inside, right? What's the outside portion? Yeah, or bracket, parentheses, cube, right? And the inside portion is just the g of x. Okay. Yeah, so we need to include that entire g of x as the inside. Okay, so now let's step through derivative rule. Outside's derivative is 3 parentheses squared. What goes inside here? Right. We're not ready for g prime. Okay. G of x times. Now we're ready for inside's derivative. So now we can take care of that derivative. Sometimes I see students trying to streamline the process, and they want to go 3 times g prime of x squared because it feels cleaner, it feels easier, but that's not what chain rule says. We got to have a separate space for the outside and for the inside derivative. Any questions so far? All right, we want to find f prime of 5. Now I can do what? What's the next step? Okay, plug in 5 in for x. So we're done with the calculus. Now we're just trying to get it down to a number. Okay. And now what's the next thing that we want to look to replace? Yeah, g of 5 and g prime of 5. Okay, so we look at the top of the page. If it's a graph, then we look at it from a graphing perspective. If it's if there's a table or if it's given to us, we just try to find those values. So g of 5 is -3 and g prime of 5 is 6. So we can just make those substitutions. Okay, multiply that out, 3 times 9 times 6. You will get to use your calculators on your test on Friday. All right, any questions there? Okay, we're going to skip over A through C, but let's just go through and make sure that we know the rules involved here. If I want to find a derivative here, I got to use what? This is product rule. If I want to find a derivative here, I'm going to use what? This is chain rule. Okay. Then for C, quotient rule. Okay. All right. All right. Let's go to last page here. want to talk about vertical and horizontal tangents and what they mean and how we can find them. So horizontal tangent, technically what that is where the slope of your graph is 0. This is where your graph is experiencing a slope of 0. Okay. And then vertical tangent is where you're experiencing a slope that's undefined. Okay. So what does that look like? Well, let's say we had a graph that looked like this. Let's say we had an ellipse. Okay, obviously, it's not a function, but it's an equation that we can still implicitly, we can find a derivative, a slope formula for a graph that looks like this. Well, your slope 0 is going to be where you can imagine horizontal tangents. So if it's a graph that looked like this, then we would expect 2 horizontal tangents, right? We're able to visually convince ourselves that we're going to get 2 slope zeros. And then how many slopes undefined are we going to have? 2 as well, right? Anytime there's a vertical tangent, that we can't create a slope for that line. So that's the vertical tangent. So what we're going to do is we're going to find the derivative equation. And typically with derivative equation, I think the way that we process derivatives usually, oh, I'm going to give it an x value or a location, and in return, I'm going to get a slope. But the other way can also apply as well. We can be targeting a slope and asking where the location is, okay? Or targeting a specific slope behavior and asking where that location is. So here's how we can do that. So if I want to find a horizontal tangent, okay, I already know what slope I'm after. I'm after slope 0. The way you can find the location is you can set the numerator of your derivative equal to 0 and solve for x, and that'll get you the location. Okay. Now, if I want to find the full order pair, I have to go one step further and plug into the original equation. Vertical tangents. This is, let's say I already know what I'm after. I'm after a slope undefined. Then I can seek out the denominator of the derivative, set that equal to 0, and that will help me find the location. Okay, so typically, I think we're more used to giving a location and asking for the slope, but it can also go the other way around where we're providing a slope that we're targeting and we're asking for the location. So, but before any of that, we have to get to the derivative before we can do all these steps. So if I want to find the derivative, what's involved here for 57? Power rule. Okay, what else? Implicit, because you see y's out of place, right? It's not a nice function where it's y equal and then x's are on the right. You see y's looking like they're out of place. Anytime you see something done to the y's or y's out of place or multiple y variables, you know you got to go through implicit, which means we got to produce dy dx within the equation and then rearrange it to get that dy dx variable by itself. All right, so let's go through our derivative process. 25x squared becomes 50x. All right, 16y squared becomes good. So we took y's derivative, so we need to include that dy dx. Go down the line. And what does that 400 become? 0. Okay. All right, so we're done with calculus. Now we're just trying to rearrange and trying to get that dy dx by itself. So I can put my dy dx terms together on the left side, push all the non-dy dx terms on the other side of the equation. Factor out the dy dx. I know there may be other common factors that can be pulled out, but we only care about isolating dy dx. We don't care if it's nice and cleaned up. So factor dy dx, and then we can move that set of parentheses over to the right side, right? Get that derivative by itself. All right, so there's my dy dx. That's my slope formula. If I give an order pair, I can ask for the slope. But for this, we already know what slope we want, right? We want slope 0 and slope undefined. So we can basically put something in place of this dy dx and look for the location, right? But here, we're going to look at the numerator and denominator separately. The numerator equal to 0 will find the location of slope 0, horizontal tangent. If I set the denominator equal to 0, then we're looking for undefined, right? Because whatever causes the denominator to be 0 is going to be undefined, in this case, undefined slope, therefore vertical tangent. So let's focus on the numerator first. I'll set the numerator equal to 0. That will help me locate these points where the slope of my graph is 0. So negative 200 minus 50x equals 0. Add 200 to both sides, divide by negative 50, and I get x equals negative 4. Any questions so far? Now, the direction says find the points. So I only have the x value, so what else do I need? Yeah, find the points, the y value, right? Because I'm missing the y value. I know the x, but I don't know the y. So back into the original, remember the original equation is always going to help you find physical locations. Now that we know, now we've matched up the slope behavior that we're looking for. Now we're going to turn around and find the location. So negative 4 in for x, you may need a calculator, but if you don't have it on you, you can just kind of follow along and copy down what I have written down in math, going through calculations. This is also on the first page or first 2 pages of your second packet, test review packet. I put the key in there. Okay, so replace every x you see with negative 4. Things will clean up nicely. The 400, the negative 800, the positive 400 will go away. So I'm just able to get it down in terms of y. Solve for y. I get, or I can factor out the 16y from my remaining 2 y terms. 16y gets factored out. I'm left with y minus 10. So I set the 16y equal to 0. I get 0. Set the y minus 10 equal to 0. I get 10. So we have two different y values with the same x. So these points are directly above each other, which we can't do in a function, but we're not dealing with a function. So we're able to now find these 2 points, negative 4, 0, and negative 4, 0, negative 4, 10. Any questions about horizontal tangent? So find the derivative, whatever way it is that you're going to get there. Set the numerator equal to 0, and that will tell you where the graph is going to experiencing these flat slopes. Right? Likewise, if I want to find vertical tangents, I can now focus on the denominator of my derivative. Right, set that equal to 0. Solve for whatever variable it's allowing me to solve. In this case, I'm going to have to solve for y because that's what's given to me. Okay, so vertical tangent. Now I'm going to focus on the denominator. Right, whatever makes my denominator 0 is going to be where my slope is undefined. So I set 32y minus 160 equal to 0. I solve for y, and I get y equals 5. But I'm trying to figure out the full order pair. So how can I find my full order pair? back into the original, right? So I have 5 in for y. Now I can turn around and solve for x. So back into the original. All right, so I inserted 5 back into the original equation. In for the y, and then that will allow me to start cleaning up. A lot of the constants will go away. I'm just left with 25x squared plus 200x. Factor out the 25x. Left with x plus 8. I have 2x values, so that tells me I have 2 different points where the graph is going to experience these vertical tangents, these places where slope is undefined. Any questions so far? Okay. One last thing to go over before we do the test review. If you can turn to page 6A, page 6A. In your new packet, this is in your new test review packet now. Anyone not here yesterday? Everyone have packet here? Okay, so this is a very specific type of setup, but I feel like once you understand how to set this up, it's all going to feel the same. And it's also a very popular type of AP exam question, so I think it's good to go through it. And also, I'm also going to put a problem like this on the test. Okay, it says finding constants to make a piecewise function continuous and differentiable. So let's just talk a little bit about what those words mean. Okay, so continuous, well, first up is that we see 2 piecewise functions, right? And they may or may not connect at 1, depending on what happens with A or B. So continuous means I want these 2 graphs to be connected. So let me just give a random example here. Let's say the graph looked like this. At 1, let's say we had a line and we had a curve. Is that going to be continuous? No. And why is that? It's because at 1, they're not having the same what? They don't have the same y value, right? But if they had the same y value, then that would be, you know, we can basically make that connect, right? So if they had the same y value, maybe the graph would look more like this. Or sorry, I'm going to put that to a straight line here. Okay, so then that will be connected. Okay, and if I want to force continuity, I would set the 2 equations equal to each other because I want the 2 of the equations to share the same y value. So that is the continuous bit of it. Okay, I want to force continuity, or I want the functions to be connected. So I'm going to have to make them share the same y value at 1. Otherwise, if it's not, then I'm not going to be able to achieve continuity. So I'm going to take my 2 equations. I have my line, I have my curve. Again, this may not be what the graph looks like, but I just want to give a visual for us to kind of work off of. Okay, so If that's true, then great. Then we have two equations that are connected and continuous. But there's something else. Okay. The something else here is that we not only need them to be connected, but we need them to be connected in a way where it's differentiable. So differentiable means there needs to be a smooth transition, a smooth curve. So right now, this graph is not really smooth, right? Because I got a slope that's negative and it's all of a sudden turning into a different slope. So what needs to happen? Well, I need this point to not only share the same y value, but they must also share the same what? Slope. They must share the same slope. If they don't share the same slope, then I'm not able to smoothly transition from one graph to the next. I'm going to get a sudden change in direction. That's going to be a sharp turn, and it's not differentiable. So in order to be differentiable, the graph must share the same slope. At their transition point. Okay, we create a situation where we're going to be looking for where the graph is going to share the same y value at their transition point, but we also must make it where they also will share the same slope at their transition point. So if we are going to force them to share the same slope, that means we have to make our way down to the what? Slope is related to the derivative, so we're going to find their derivatives and then do what with them? Set them equal. So that's the key right here. That's what makes this problem different than just setting the equations equal. We have to understand, oh, differential, I got to involve derivative, I got to involve slope, and that's what I'm going to do. I'm going to have to set their derivatives equal. Okay, so that's the challenge. The challenge is reading the problem and understanding, oh, I got to involve derivatives, and this is what I'm trying to achieve. So we need to find their derivatives and set them equal to each other. Now, you're going to treat a and b like you would if it was a 3 or 5 or 7. It's just a constant. Okay, so if you're having trouble trying to find the derivative of a or b, just pretend like it's a number and do the same thing that you would do with that number. So let's look at ax plus 3. What's the derivative of ax? A. Just a, right? Imagine if it was 2x or 5x. You would just keep the coefficient and drop the variable, right? So ax will become a, and the 3 goes to a 0. So that's one side of the equation. That's the derivative of my top piecewise. My second piecewise, 3x squared plus x plus b. So let's go down the line here. 3x squared becomes 6x. X becomes 1. And b becomes 0, right? Doesn't become 1. I know it may feel like it because b looks like a variable, but b is a constant. So we'll go to 0. Okay, so I'm going to drop that 0. That's not going to mean anything. Now, I want to solve for a and b, but is there any other information that I can put into to help me out? Where's the center of my problem here? 1, because that is always going to be provided for you, right? That is the potential breaking point between the two graphs, and we want to make it so that these two graphs will connect and transition smoothly. So we know the x value in question is 1, and that's going to be all the x values. So just go ahead and replace every x value with 1, and we should be able to then algebraically try to solve for a and b. The hard part is the setup. The setup, understanding that I need two equations. One where I set the piecewise equal, one where I set their derivatives equal, replace the x with whatever that transition point is, and then the rest is just algebraically solved. Okay, the reason why we need two equations is because if we didn't, then we're going to be left with two constants. So we need two equations for one to help the other one out. So here, the first one, I'm kind of stuck, a equals 1 plus b. I have two missing values, so I'm going to go to my other equation to see if that will help me out. All right, what's a equal to? So if a equals 7, then I can turn back and help me solve for b, right? So therefore b equals. Okay, so any questions with that process there? Okay, so see if you can do number 3 on your own. If you can do number 3 on your own, that means you should feel comfortable with this process. It's going to be very specific. It's the same thing you do every time. Continuous and differentiable, we needed to create two columns, one for the equation and one for their derivatives. Now, there is a bit of a wrinkle that I want to kind of point out is that sometimes on the AP exam problem, they will leave out this word continuous. Why is it that they're able to leave out that word continuous and still expect you to do everything? Be differentiable, be continuous. Good. In order to be differentiable, you must be continuous. And so that's why sometimes the problems say, well, there's no need for me to duplicate my wording. I'm just going to say differentiable. But if you only see the word differentiable, as a student, I think it's helpful to say to yourself, okay, continuous and differentiable. And that way you can focus on the idea that, okay, continuous means connected. We're going to have to work with the equations. Differentiable, smooth curve, slope related. We're going to have to involve their derivatives. So we still want to categorize it as two different things, even though they're only using that word differentiable. But yeah, continuous and differentiable. Okay, so set your equations up. Talk over the answers, but then the key is on the back. You can check your progress. If you're good with this, you should be comfortable when you see this on the test as well. You know exactly how to move through this problem. It's the
I was reading. Yeah.
Okay, so set your equations equal. Turn to the other second column. Find the derivatives and set them equal to each other. Replace every x with, in this case, -1, because that's -1 is the point in question where we want the transition to occur between the two branches. And once you replace all the x's with -1, you're going to be down to two equations and solve for one and use one to solve for the other. Yeah, and then yeah, so I pointed out a couple of tricky things. Another tricky thing is sometimes they leave out the word continuous, and you just have to understand, okay, I cannot have differentiability without continuity, and if it helps to verbalize that, then you may need to add that to that statement, and then force yourself to create two equations to work with. All right, any questions? So you'll see a problem like this on the test, and it'll be worded the same, very, very similarly, and you know that word differentiable with piecewise functions will just tell you how to set it up, right? It tells you, oh, I gotta create my equations, set my equations equal, set my derivatives equal, replace every x with whatever the number is, and then go through your algebra. All right, let's go to test review, page 11. Okay, number one says the average, okay, that's the key word there, average rate of change of the function on the interval from 1 to 3 is. So you're going to treat this like you would if you saw if it was average velocity. So how do you think we can set up to find average rate of change? Just find the what? Okay. So the thing is, there's no derivatives here. We're just going to find, yeah, just slope between the endpoints. Okay, so just the slope between the endpoints. The key word there telling us that there is no calculus is that is the average rate of change, right? We're not looking for the instantaneous or the exact rates of change at those moments. We just want to know what is the slope between the endpoints. So just change in position over the change in time. So use your calculator again, or it's not too bad here. And find f of 1, f of 3. So f of 3 is 3, f of 1 is 3. 3 minus 3 is 0, 0 over 2 is 0. So my average rate of change is 0. Right. What's different about number 2? Right, so let's say the graph looked like this, right? And the slope between the endpoints was 0. But now it's asking for the instantaneous rates of change. So it's asking, oh, at the endpoints, what are the slopes going to be? And we see that the steepness is going to be very different at those endpoints, right? So now we got to involve calculus. Now we have to find the slope formula and find those specific slopes at those particular points. So instantaneous rate of change, we need to find our f prime because we want to know the exact steepness at a specific point, not just between 2 points. So find the derivative first. And you're going to get 2 answers, right? Because you have 2 different slopes at 2 different points. Okay, number 3. We need some space for this, so if you're able to create some space or put this on a separate sheet. Number 3 says find, that notation means find the second derivative, d2y over dx2. Sorry guys, it keeps jumping back and forth. Find the second derivative for y equals square root of x squared plus 1. Okay, but before we can find the second derivative, we first have to find the first derivative. Okay, so action is bad. Okay, so for y equals square root of x squared plus 1. Okay, what would I need to involve, or how would I rewrite this so I can see what rule I need? Okay. Okay, so what rule do you think we have to involve if we want to find the derivative? Chain rule. Okay, so we're going to find our outside and inside portions, find their derivatives. Connection issue is better here. Okay, so outside, inside. Outside is the parentheses of the 1/2. Inside is the x squared plus 1. Okay, outside's derivative. 1/2. Parentheses to the negative 1/2. What goes inside here? Okay, x squared plus 1. We're not ready for its derivative yet. Now that we're done with the outside, now we have a separate space, and that separate space is for the inside, so times 2x. Okay, so we'll do some cleanup. So our dy dx, or our y prime, is this cleaned up. Okay, so what can I do to clean this up here? Anything can go, does anything go away? Yeah, what happens? Yeah, 2 goes away, right? 1, 2 above, 1, 2 below. And what else can I do? Yeah, bring the parentheses to the denominator, x squared plus 1 to the 1. So we're halfway there. That's our first derivative. Now, to get to the second derivative, I have to look at what I have and decide what is involved to get to my second derivative in terms of what's available to me. Now there's going to be a combination of rules that's involved. Can you name what those rules could be? Chain rule and quotient rule. Okay, so which one is going to come first? Okay, so the way we decide, okay, you're right, quotient rule. What we decide is you look at the parentheses. If parentheses is over the entire expression, that means chain rule has a further reach than the other rule. So the larger rule that has a larger impact is going to come first. The rule with a larger impact. But here, the parentheses is only over the denominator. So that means there's a larger rule that has a further reach, and that is quotient rule. So quotient rule is going to come first. And then once you're inside quotient rule, then you can do chain. Now, some students have asked, wait, what if I just brought this up and went through product rule? You could go through product rule, and within product rule, go through chain. But I like to do it this way because I know there's a denominator involved, and it's going to end up with a denominator. If I went through product rule and chain rule, I'm going to have to get it back down to my numerator and denominator anyway. So what is not wrong is if you did product and chain, I just find it more convenient to do it this way. Yeah, that's just my preference. But you could definitely do this product and chain and get down to the same answer. So so quotient is going to come first, right? So I'm going to set it up, F top and G is the bottom. Okay, F prime G plus, F prime G minus FG prime. Don't forget, if you're doing quotient rule, you got to divide by denominator squared. Okay, so F prime. This what? This one. G function, no changes. Back to F. And G prime, we see the parentheses with terms inside and exponent outside. Now we're going to see chain rule getting activated here. All right, so just looking at the denominator there, what's the outside portion? Parentheses the 1/2, right? Inside portion is the x squared plus 1. And we go through chain rule just for that part right there. So outside derivative, 1/2 parentheses to the negative 1/2. Keep the inside intact. Times what? What's inside derivative? 2x, right? X squared becomes 2x, 1 goes to 0. So we took care of G prime, we took care of the chain rule portion of this problem. Now we divide it by denominator squared. Okay. Okay, what's that going to do here? 1/2 with the square. Yeah, it just becomes 1, right? Anytime I have two exponents next to each other, I'm going to multiply them. Okay, so this is where we have the derivative, but we're going to continue to see if we can get it down to a little bit cleaner form to match one of the answer choices. Okay, the messiness comes from this part right here, right? Got some negative exponents to deal with. The question is, I want to deal with that negative exponent. I want that to be a positive exponent. I want to push it to a different place. The question is, can I push this parentheses with the negative exponent down to this denominator and let these two share the same space? Why is that?
N minus.
Yeah, if we follow this whole thing, we do see multiplication on both sides, but if we follow this, it's all connected to that minus sign. And that basically prevents us from being able to push this down across this big denominator line. Now, what we can do is we can create a denominator within this space, but that's going to create a complex fraction, and that's what I want to go through. I want to talk about how to clean up that complex fraction. So I'm just going to do some cleanup here. Now, I'm just going to do some cleanup within this space. what is that going to combine? Well, do you see anything that goes away, cancels out? 1/2 and the 2, right? One's in the numerator, one's in the denominator. Okay, I can merge these two x's to be what? X squared. And I can push this to the denominator within this little space here. So x squared over x squared plus 1 to the 1/2. Okay, now this is all over my cleaned up denominator, which is x squared plus 1. Any questions so far? Now, just like with unit 1, when we had those complex fraction problems, we turned our attention to try to clean up this portion, right? If I can get this to be a common denominator and merge together, then I'll have a much easier time working that x squared plus 1 in. So I'm going to step to the side and try to figure out how to get the two of them to share a common denominator. So I don't see anything below here. I'm going to put a 1 below. Now I'm going to ask myself, what's my common denominator? This x squared plus 1 to the 1/2, right? I'm going to ignore this bottom here. I'm just going to focus my attention on just this part. Okay, so we're in agreement that our common denominator is x squared plus 1 to the 1/2. The next step is we have to balance our fractions, right? Has anything changed between this denominator and this denominator? 1 to x squared plus 1, right? So what have we done? We've multiplied with x squared plus 1 to the 1/2 to reach this point. So I need to do the same thing to the top here. So if I need to make an adjustment with my denominator, I also need to balance it out with the numerator. So if I multiply these two together, these are the same. So what can I do with the exponents? Add them, right? So 1/2 plus 1/2 is 1. So I'm left with x squared plus 1. Now, any changes between this denominator and this denominator? No changes, so the x squared can just stay. Okay. So now I've achieved common denominator. I can merge these together. So if I merge these together, I can combine my terms here. What happens with the x squared? Goes away. X squared minus x squared is 1, or 0, sorry. So I'm left with 1 over x squared plus 1 to the 1/2 all over x squared plus 1. So we're a lot closer now, right? But dividing by a fraction is same thing as, sorry, dividing by a number is same thing as what? Multiplying by the reciprocal. If I bring this up as, rather than divided by x squared plus 1, I'm going to multiply by the reciprocal. So times 1 over x squared plus 1. Well, the nice thing is my denominator matches. So if I want to multiply these two bases, I can just do it with the exponents, add them, right? So there's a hidden 1 there. 1/2 plus 1 is 3/2. So there's my cleaned up second derivative. Okay, we'll continue with the rest of review worksheet 1. Try to get through worksheet 2. I'll have a help session tomorrow, 5th period. I had a help session this morning, and I put the recording on the website. Okay, hope you get your phones. Test will be on Friday. That's right.
Why did you still?
If I multiply these two together, I'm going to add exponents because they're the exact same base. So what's 1/2 plus 1/2? 1. And 1 it's the same thing as just swapping.
Oh, we don't. I guess they show you this time.
Thank you.